Look at this complex landscape. It is entirely synthetic, generated in a matter of seconds by artificial intelligence. That same underlying technology is currently re-engineering the $3 trillion automotive sector, driving factories toward complete automation. And in laboratories worldwide, high-performance computing is analyzing massive datasets at the molecular level to design entirely new medical treatments. Yet none of these breakthroughs trace back to a traditional data science laboratory. They originate from a company that started out focused on something else entirely. For years, researchers knew that training vast neural networks required massive processing power, but traditional computer processors evaluated information sequentially, making the required mathematics practically impossible to execute. This chart illustrates the crisis. As computing demand grew exponentially, the efficiency of standard processors flatlined. Data centers were already consuming up to 2% of global electricity, hitting an unsustainable power ceiling. Moving forward required a complete architectural overhaul. The entire field of artificial intelligence was stuck waiting for a radically different physical engine. Back in the 1990s, NVIDIA was trying to solve a very specific problem: making video games look real. Rendering 3D environments requires calculating light, shadow, and geometry for millions of pixels simultaneously, 60 times a second. This diagram compares the approaches. Instead of one large processor handling tasks sequentially, NVIDIA built chips with thousands of tiny cores processing massive amounts of data simultaneously. They called this parallel processing, and its sole purpose was generating virtual worlds. The physical result of this engineering was the Graphics Processing Unit, or GPU. By engineering the hardware to render artificial environments, they had inadvertently created the exact architectural foundation needed to process the massive datasets used in modern deep learning. The bridge is the mathematics. The parallel operations used to calculate the depth of a digital shadow are identical to the weight adjustments used in training a neural network. When researchers realized they could route their data through GPUs, training times for complex models dropped from months to mere days, providing the necessary speed for the AI revolution to begin. At a time when they were already a dominant provider for gaming graphics, NVIDIA pivoted their focus toward data centers and high-performance computing, a strategic move that required redesigning their entire software stack for a market that barely existed. This specialized approach allowed server racks to process vastly more information per watt, bypassing the energy bottlenecks that had stalled traditional data centers. They scaled product lines upward, shifting from manufacturing standalone graphics cards to designing massive, integrated facilities, providing the heavy hardware required to process global data. By supplying this indispensable physical infrastructure, they positioned themselves as the primary engine driving the entire AI economy. This era of accelerated computing has now arrived as a new computing platform, driven by the sudden explosion of generative AI. This timeline shows how computing has transitioned over decades. Today, generative AI has moved past being a specialized tool to become a primary foundation for software and services. Right now, their Omniverse platform connects physical manufacturing directly with digital twins, optimizing heavy global industry through high-fidelity simulations. The architect steering this constant structural evolution is CEO Jensen Huang. He often describes his organization by stating, "We are a learning machine." This culture of adaptation ensures they consistently anticipate the physical demands of complex software before the market realizes they are necessary. NVIDIA now manufactures the physical foundation that global technology relies upon to function.